A defining moment that showed general relativity was correct occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the Sun. According to the theory, the Sun's massive gravity would cause starlight to bend slightly. During the eclipse, the observations perfectly matched Einstein's predictions, establishing the validity of the theory. Just as motion can alter our experience of time according to special relativity, gravity also affects time. In regions of intense gravity, time moves more slowly compared to areas with weaker gravity. For instance, if you were standing close to a massive object like a black hole, your clock would tick more slowly than one set far away from that immense gravitational pull. General relativity introduces black holes, regions where gravity is so extreme that nothing, not even light, can escape. The edge of a black hole is called the event horizon, which acts as a point of no return. Once something crosses this boundary, it is pulled into the black hole with no chance of escape. Einstein's theory of general relativity has significant implications for understanding the structure of the universe. Initially, Einstein introduced a cosmological constant to his equations because he believed the universe was static. However, when it was discovered that the universe is expanding, he called it a blunder. The concept of an expanding universe, rooted in general relativity, is central to the Big Bang theory, which explains the origins of the cosmos. Another major concept from general relativity is gravitational waves, ripples in the fabric of spacetime caused by massive objects moving rapidly, such as when black holes or neutron stars collide. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, providing further confirmation of Einstein's theory. Over time, scientists have conducted numerous experiments to test general relativity, and each time it has proven correct, whether through studying planetary motion, light bending, or gravitational wave detection. While gravity seems obvious to us in daily life, physicists often challenge established theories. For instance, some researchers propose ideas like modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at slow speeds, especially in galaxies, without requiring dark matter. Instead of adding invisible matter, MOND proposes that gravity strengthens at low speeds. The debate over gravity also involves dark matter and dark energy, introduced to explain certain cosmic phenomena. Critics argue that alternative theories might explain these observations without invoking unseen entities. The quest for a deeper understanding of gravity continues, and some scientists believe we may eventually discover a new framework to replace conventional ideas about gravity. Time is a complex, multi-layered puzzle. In physics, our best understanding evolves with new ideas and evidence. Brian Cox's latest theories on time, for example, might bring us closer to a discovery that fundamentally reshapes what we know about the universe. As we advance in understanding time and gravity, we face new frontiers. Modern advancements like quantum mechanics and the search for a unified theory of everything push us closer to unraveling the deepest mysteries of the universe. Quantum mechanics, which governs the behavior of the smallest particles, introduces a realm of probabilities rather than certainties. This microscopic world behaves very differently from the macroscopic universe governed by Newtonian physics or Einstein's relativity. Scientists are striving to merge these two realms into a unified theory, a framework that explains both the very large and the very small. For example, such a theory could reconcile the nature of time as we understand it on a cosmic scale with the strange behavior of particles at the quantum level. Renowned physicist Stephen Hawking dedicated much of his career to exploring these questions, working to unify these two perspectives. His efforts, alongside others, have opened exciting possibilities, but a complete theory of everything remains elusive. The interplay of time, space, and gravity has been greatly influenced by technological advances. Instruments like the Hubble Space Telescope and, more recently, the James Webb Space Telescope have allowed us to observe galaxies that formed billions of years ago. By studying how light and time behave at such vast distances, we gain insights into the universe's evolution. Experimental tools like the Large Hadron Collider (LHC) also help test these ideas on a fundamental level. By smashing particles at nearly the speed of light, the LHC allows us to probe the forces and particles that make up the universe. This could lead to new discoveries about how gravity works at quantum scales or how time behaves under extreme conditions. The study of black holes, in particular, continues to provide groundbreaking insights into spacetime. The first-ever image of a black hole, captured by the Event Horizon Telescope in 2019, marked a historic moment in science. Such discoveries challenge the limits of our understanding and force us to rethink the nature of time, space, and gravity. In everyday life, the effects of relativity are usually so subtle that they go unnoticed. However, on larger scales, near black holes or at near-light speeds, these effects become crucial. As we continue to explore the outer reaches of space and study phenomena like the universe's expansion, we edge closer to uncovering the ultimate nature of reality. The universe holds the potential for time travel and an understanding of the behavior of gravity at extreme scales. One day we may uncover new laws of physics that could drastically change our conception of the universe. Perhaps one of the most fascinating ideas that continues to captivate researchers is time travel. While it is often the stuff of science fiction, the real science behind time travel is rooted in the very theories we have discussed: special and general relativity. Under certain conditions, for example, the presence of a massive rotating object or the bending of spacetime around a black hole, hypothetical physicists have proposed scenarios where time loops or bends could exist, allowing travel backward or forward in time. However, these ideas remain theoretical, and many paradoxes arise when attempting to grasp such possibilities. Newton's understanding of gravity was sufficient to allow us to travel from Earth to the Moon. Yet, have you ever found yourself lost in the ticking hands of time, wondering if our understanding of it is merely the tip of the temporal iceberg? Perhaps his discovery is not just a theory but a key to unlocking the mysteries of the universe, revealing a cosmos more complex and inspiring than we ever imagined. How does Brian Cox's new hypothesis challenge our conventional understanding of time? And what are the potential implications for our perception of reality? Join us on a fascinating exploration through the fabric of time itself as we delve into Brian Cox's recently revealed groundbreaking hypothesis on the nature of time in the vast universe. Around us, mysteries are waiting to be uncovered, some involving enigmatic phenomena like time and gravity, which are fundamental aspects of our reality. Imagine a reality where time behaves oddly, slowing down or speeding up. Likewise, the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, which revolutionized our understanding of time and gravity. Einstein, a renowned name, introduced a new perspective on the universe through his theories of relativity. His work laid the foundation for understanding how time behaves under different circumstances, especially when traveling at incredibly high speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of space and time. In simple terms, it tells us that the laws of physics are the same for all observers who are not accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous idea that time can dilate or slow down under certain conditions. One fascinating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, a beam of light bounces between two mirrors perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a diagonal path. Here's the intriguing part. The time it takes for the light beam to travel this path should be the same for both the observer inside the spaceship and the one outside. However, because the path is longer for the external observer, it appears to take more time for the light to complete its journey. This apparent time difference is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. Understanding how things change when they move fast, known as relativistic effects, is not just a theoretical idea. Scientists use large machines called particle accelerators like the Large Hadron Collider to make particles travel nearly as fast as light. When objects move this fast, we must account for time in a special way to make accurate predictions and measurements. Albert Einstein's special theory of relativity challenges our everyday intuitions. It asserts that the rules of physics are the same for everyone, even if they're moving at different speeds. This is different from our everyday experience, where we might think that adding speed makes something move faster. But Einstein's theory states that nothing can travel faster than the speed of light. This perspective also shows that events that seem simultaneous to us might not appear that way to someone moving at nearly the speed of light. Another concept from this perspective is length contraction, which means that if an object is moving, it appears shorter in the direction of its motion when viewed from a stationary point. Then there's the famous equation, E equals mc squared, which shows that energy and mass are interchangeable. This principle is crucial for understanding how particles behave at high speeds and for phenomena like nuclear reactions. In practical terms, special relativity isn't just theoretical. It's used in everyday technology like GPS. When GPS satellites send signals to your device, they are moving, and because of this motion, time behaves slightly differently for them. If we didn't account for this time dilation effect in GPS calculations, navigation would be inaccurate. Special relativity teaches us that time is not the same for everyone, everywhere. Depends on how things are moving. This idea challenges our conventional understanding of space and time, showing that our everyday perceptions of the universe are limited. Now, enter Einstein's general theory of relativity, introduced in 1915. This theory delves deeply into the relationship between gravity and the structure of the universe. It overturns the old notion that gravity is merely a force pulling objects from a distance. Instead, it explains that gravity occurs because space and time are curved or warped. It's as if gravity is not a mysterious force but the natural way objects move in the universe. According to Brian Cox, understanding general relativity requires thinking of the universe as a four-dimensional entity combining 3 dimensions of space and 1 of time. In this framework, massive objects like stars, planets, and even us shape the structure of space and time around them. This shaping is what we perceive as gravity. Imagine spacetime as a large, stretchy fabric. When a heavy object like Earth is placed on it, it creates a dent in the fabric. If you place a smaller object like a ball near Earth, it will move toward the dent. This is analogous to how objects behave due to gravity, not as a mysterious force but as a response to the curvature of spacetime. General relativity provides a powerful explanation for the movements of planets in our solar system, including Earth's elliptical orbit around the Sun. This is a departure from the old idea of gravity as a pulling force, which struggled to explain planetary motion. Instead, the new idea is that space and time are curved like a flexible fabric, which better aligns with our observations. The nature of gravity and the warping of spacetime. Einstein's general relativity not only explained planetary orbits but also predicted phenomena such as gravitational time dilation and black holes. The concept that massive objects warp spacetime means that time itself is affected by gravity. The stronger the gravitational field, the slower time moves relative to a weaker gravitational field. For example, if you were near the surface of a neutron star, a superdense remnant of a collapsed star, time for you would pass much more slowly compared to someone on Earth. This effect has been confirmed through experiments, such as placing highly precise atomic clocks at different altitudes. The clock at a higher altitude, experiencing weaker gravity, runs slightly faster than one closer to Earth's surface. One of the most extreme examples of gravitational time dilation occurs near black holes. A black hole's gravity is so intense that it distorts spacetime to the point where nothing, not even light, can escape its pull beyond the event horizon. According to general relativity, time essentially comes to a stop at the event horizon from an outside observer's perspective. If an astronaut were to approach the event horizon, they would appear to slow down infinitely, never quite crossing the threshold, at least from the viewpoint of someone watching from a distance. Brian Cox's perspective on time and the universe. Brian Cox, a leading physicist and science communicator, has taken Einstein's ideas and expanded upon them in discussions about the nature of time. He suggests that time is not a fixed, universal constant but a dynamic entity woven into the fabric of the cosmos. His interpretations align with general relativity, emphasizing how time is not an independent phenomenon but intrinsically linked to gravity and motion. One key idea Cox explores is whether time itself might emerge from the fundamental interactions of the universe rather than being an absolute, pre-existing structure. Some modern physicists propose that time could be a byproduct of deeper quantum processes, perhaps even an illusion arising from our perspective as observers within spacetime. Cox also discusses how our understanding of time travel, though highly speculative, is grounded in serious physics. While traveling back in time creates paradoxes, such as the famous grandfather paradox, traveling forward in time is scientifically possible due to time dilation. Astronauts aboard the International Space Station, for instance, age slightly slower than people on Earth due to their high velocity and weaker gravitational field. Could we manipulate time? The possibility of controlling time, slowing it down or even reversing it, remains largely theoretical. However, physicists have explored potential mechanisms that could allow four closed time-like curves, or loops in spacetime that theoretically permit time travel. These scenarios often involve extreme conditions, such as rotating black holes, Kerr black holes. Some solutions to Einstein's equations suggest that if a black hole is spinning rapidly, it might create a region of twisted spacetime where time loops are possible. However, practical travel through such a region remains speculative. Wormholes. A hypothetical shortcut through spacetime, a wormhole could, in theory, connect distant points in space and time. However, natural wormholes have never been observed, and maintaining a stable one would require exotic matter with negative energy, something we have yet to discover. Cosmic strings. These theoretical one-dimensional defects in spacetime, left over from the early universe, could potentially distort spacetime in such a way that time travel is feasible. While these ideas are intriguing, they are far from being practical or proven. The challenge lies in the immense energy and stability conditions required to manipulate spacetime on such a scale. The future of time exploration. Despite the uncertainties surrounding time travel, our understanding of time continues to evolve. Scientists are now exploring the intersection of general relativity and quantum mechanics, aiming to develop a theory of quantum gravity. This could provide deeper insights into the true nature of time, spacetime, and gravity. One leading contender is loop quantum gravity, LQG, which suggests that spacetime itself is quantized, meaning it consists of tiny, discrete units. If this is correct, it could imply that time, like space, is not continuous but emerges from more fundamental quantum interactions. Another approach, string theory, posits that reality consists of tiny vibrating strings existing in higher dimensional space. Some versions of string theory propose that time behaves differently at microscopic scales, potentially offering new insights into time's true nature. Final thoughts. As Brian Cox and other physicists continue to explore these mysteries, one thing is certain: our understanding of time is far from complete. Whether time is an absolute entity, an emergent property, or something even stranger, future discoveries in physics could revolutionize how we perceive reality. Time may not be as rigid as we once thought. Instead, it might be a fluid, dynamic aspect of the universe, one that bends, stretches, and perhaps, under the right conditions, even loops back on itself. Who knows? In the future, our understanding of time may lead to breakthroughs we can scarcely imagine today, perhaps even unlocking the secrets of time travel.